Let's jump right into this explainer. Have you ever wondered what exactly happens behind the scenes when you fire up a VPN? We're talking about that invisible, highly secure secret handshake that protects our data across the open internet. Every single time you connect to a secure corporate network or tunnel your traffic, this ridiculously complex negotiation happens, literally in fractions of a second. Today, we're focusing entirely on the Internet Key Exchange Protocol, better known as IKE, and exactly how it builds these secure connections right from the ground up. We've got a lot of really fascinating networking concepts to get through today. Here's our roadmap. We'll start with the VPN handshake problem, look at IKEv1 Phase 1 setup, and then Phase 2 essays. After that, we'll dive into the IKEv2 evolution, check out IKEv2 message exchanges, and wrap up with maintaining the tunnel. Section 1, the VPN handshake problem. To kick things off, we really need to understand the fundamental issue at play here. Before a VPN can securely transfer any data, it absolutely has to validate the identity of the other party, but it has to do this without exposing its own secrets to anyone who might be snooping on the wire. So, the crucial takeaway here is getting a solid grasp on two specific terms, because the entire purpose of IKE is to negotiate these things called Security Associations, or SAs. You can think of an SA as a really strict, mutually agreed upon contract. It dictates the exact cryptographic keys, the hashing algorithms, and all the specific rules that both peers are going to use to protect their communication. It's pretty simple. Without a successful IKE negotiation, there's no SA. And without an SA, there's no secure tunnel. Period. In the real world, an SA is actually made up of IKE proposals, IPsec proposals, and overall policies. Essentially, the two peers have to sit down and agree on the IKE proposal to secure their control channel, then the IPsec proposal to secure the actual data, and finally, the overarching policies that define exactly what traffic is even allowed to trigger and traverse this tunnel in the first place. Okay, moving on to Section 2, IKEv1 Phase 1 setup. Let's take a look at our first major protocol, IKE version 1, and see exactly how this initial phase builds a bidirectional control plane channel, which is known as the ISAMP SA. IKEv1's main mode actually breaks this negotiation down into 3 distinct two-way exchanges. That's 6 messages total. In packets 1 and 2, the initiator and responder are really just feeling each other out, figuring out if they speak the same cryptographic language by matching up encryption and authentication policies. Then, packets 3 and 4, well, that's where the heavy mathematical lifting happens. They execute a Diffie-Hellman exchange to independently generate a shared secret key. And because they finally have this shared key, packets 5 and 6 are fully encrypted. This lets them safely hand over their identities and authentication hashes to each other with absolutely zero chance of anyone on the open internet seeing who they are. But as you can imagine, sending 6 back-and-forth packets can introduce some annoying latency. When you compare main mode to aggressive mode, you're essentially looking at a classic trade-off between strict identity protection and faster connection speeds. Aggressive mode compresses Phase 1 into just 3 packets. The initiator throws its policy, its Diffie-Hellman public key, and its identity over the wall all at once. The catch? Because that shared secret key hasn't been derived yet, those identities are exchanged completely in the clear. So yeah, it's definitely faster, but it's a whole lot less secure if you care about identity privacy. Right, that brings us to Section 3, IKEv1 Phase 2 essays. Once that Phase 1 control channel is fully authenticated and locked down tight, we immediately transition right into Phase 2 of IKEv1. This is where the actual data tunnel gets built. Phase 2, which you'll often hear called quick mode, takes the keys and that secure ISAC assay generated back in Phase 1 and uses them to negotiate the actual IPsec Security Associations. These are the crucial assays that will encrypt your real network traffic. We're talking your emails, your file transfers, all the good stuff. And because the channel is already secured by Phase 1, quick mode can super efficiently negotiate the encapsulating security payload or authentication header parameters to just get your data flowing. But wait a second. Going through 6 whole packets for Phase 1 main mode, and then at least 3 more packets for Phase 2 quick mode, we're looking at a minimum of 9 packets just to say hello and establish a connection. That is computationally heavy, and honestly, it's pretty slow, especially if you're talking about mobile devices constantly bouncing between different networks. It really begs the question, isn't there a faster, more efficient way to handle this entire handshake? Which perfectly tees up Section 4. The IKEv2 evolution. This successor protocol was designed from the ground up specifically to solve those exact latency and complexity headaches we just uncovered with IKE version 1. IKEv2 is a real game changer because it completely abandons that rigid, clunky Phase 1 and Phase 2 structure. Instead of demarcated phases, it squashes the negotiations into a highly fluid, combined exchange. At its best, an IKEv2 tunnel can be fully established in as few as 4 packets. There's no more messing around, configuring main mode or aggressive mode. The protocol just handles it and optimizes the exchange natively. Let's get into Section 5, IKEv2 message exchanges. We really need to break down exactly how this elegant, modern piece of engineering operates out in the wild. In just 4 short messages, the whole shebang is done. The first 2 messages make up what's called the IKE saw-init exchange. This establishes the secure channel right out of the gate by negotiating cryptographic algorithms and executing that Diffie-Hellman exchange. Everything after this very first exchange is totally encrypted. Then, messages 3 and 4 make up the IKE auth exchange. This is where the peers authenticate those identities they established in Step 1, usually using certificates or pre-shared keys. But here is the absolute genius part. While they are authenticating, they are simultaneously negotiating the parameters for the actual data tunnel. This quote really hits the nail on the head regarding the brilliance of IKEv2. After the IKE_auth exchange is complete, both peers already have one SA built and ready to go. By the time packet 4 is finished, your data is literally ready to flow. That initial IPsec child SA is baked right into the authentication step. It's just a massive leap in efficiency over the old IKEv1 way of doing things. Finally, we arrive at Section 6, maintaining the tunnel. Because, as it turns out, building the tunnel is really only half the battle. Making sure it stays secure, active, and cryptographically sound requires some constant, behind-the-scenes maintenance. IKEv2 uses 2 very specific message exchanges to manage the tunnel dynamically. First, you have the informational exchange, which is kind of like the heartbeat of the connection. It handles liveliness detection, reports any weird errors, and quietly cleans up old, expired connections. Then you have the Create Child SA exchange. You can think of this as the IKEv2 equivalent to IKEv1's quick mode, but it's only ever used after the initial setup is done. It allows the peers to spin up brand new, additional data tunnels or generate fresh cryptographic keys for existing SAs, all without ever interrupting your active secure connection. And speaking of fresh keys, cryptographic keys have a limited lifespan, right? That's to prevent someone with enough time from cracking them. Well, the protocol uses some pretty clever methods to rotate them seamlessly. Inline rekeying establishes new keys without dropping the tunnel. But if the peers need to completely re-verify their credentials from scratch, they use a brilliant make-before-break strategy. They actually go ahead and establish a parallel, overlapping security association with the new keys before they tear down the old one. For you, the end user, this means absolutely 0 traffic loss. You won't notice a thing. As we wrap up this explainer, I want to leave you with the really fascinating vulnerability that's ironically built right into this amazing efficiency. Think about it. During that very first IKE SSA init exchange, the responding server has to perform some seriously heavy, computationally expensive Diffie-Hellman math. This means an attacker can just flood the server with spoofed initiation packets, forcing the responder to burn up all its CPU cycles calculating keys for a connection that doesn't even exist. So while IKEv2 is incredibly fast and efficient, it leaves us with this provocative thought. Just how fragile and initially vulnerable are our most secure internet handshakes? Definitely something to chew on. Thanks so much for joining me on this deep dive into the IKE protocol.